Hello everyone, BeaconBot back again, here to read some more AI papers. I'm either going to do a rant or read a paper every day. Today, we got a doozy. Titans, learning to memorize at test time. Had some friends recommend it. They were shocked I haven't read it, so I felt very, very stupid. So let's dive in. A little bit of a longer one. There's some math. I'm not going to be able to understand it. I've pulled the PDF into Markdown, and so we're going to cut this thing up inside of our little NeoVim instance right here. Here, let's even make this screen just the littlest bit bigger. Ooh, yeah, look at that. I'm smaller. We can make the screen bigger. There we go. Cutting right into my shoulder here. The littlest bit smaller. We do these edits live, okay? Did I end up making it bigger? Okay, whatever. That's good enough. Okay. So, Ali Barros, Pelin Zong, and Vahaba Miranit. Google research. I tried my best, people. Abstract. Over more than a decade, there has been extensive research effort. Ooh, there's a spelling mistake on the first line. Oh, no, never mind. It copied over weird. Why? Look at 2 F's became 1 F. I don't know why that happened. Interesting. There's been an extensive research effort on how... Look, 2 F's became 1 F again. We've got a 2 F into 1 F problem. Okay. Interesting. There might be... something we've done in our conversion has messed something up going from PDF to here. It's okay. We're gonna not focus on these spelling mistakes, okay? Okay. Sorry, everyone. We're doing these live, okay? Look I'm listening to Steve. The Steve Hauschild. I don't know how to pronounce anything. I don't know how to say anything. This is Strands. I'm struggling so much. I'm just going to start from scratch. I'm going to start over. We're going to go to Die in Fascination, one of my favorite songs on this album. And then we'll start from the beginning. Titans. Learning to memorize at test time. Abstract. Over more than a decade, there's been extensive research effort on how effectively utilize recurrent models and attentions. While recurrent models aim to compress the data into a fixed-sized memory called hidden state, attention allows attending to the entire context window, capturing the direct dependencies of all tokens. Oh boy. Okay, there's been a very extensive research effort on how to effectively utilize these recurrent models and attention. I understand that. Now, recurrent models, they aim to compress the data into a fixed memory size called hidden state. Attention allows attending to the entire context window, capturing the direct dependencies of all tokens. Okay. This more accurate modeling of dependencies, however, comes with a quadratic cost, limiting the model to a fixed length context. We present a new neural long memory module that learns to memorize historical context and helps an attention to attend to the current context while utilizing long past information. Interesting. They're saying that, yo, dog, we're going to be able to have longer contexts here and be able to go back further to pull information into attention at the right time. Instead of when we have this, but right now, you know how it is when you throw like a giant, huge document at something and then you realize, wait a minute, it actually is only returning information about the last 20% of the doc and not actually the beginning of the doc, even though it took the whole doc in and it said it processed it properly. We show that this neural memory has an advantage of fast parallelization training while maintaining a fast inference. From a memory perspective, we argue that attention, due to its limited context but accurate dependency modeling performance as a short-term memory, while neural memory, due to its ability to memorize the data, acts as a long-term, more persistent memory. Based on these two modules, we introduce a new family of architectures called Titans. Whoa, Titans. And present 3 variants to address how one can effectively incorporate memory into this architecture. Our results, our experimental results on language modeling, let's see, common sense reasoning, genomics, and time series tasks show that Titans are more effective than transformers in recent modern linear recurrent models. They further can effectively scale to larger than 2 million context windows with a higher accuracy in needle in the haystack task compared to baselines. Okay, lovely. Just delete all that. It's gone. I already read it. The true art of memory is in the art of attention. That is so true. If you didn't pay attention to something, how are you going to even memorize it? Samuel Johnson, 1787, bar. All right. Transformers. Pure attention-based architectures, 2017, have firmly established... Dude, there's so many missing words. It's okay. This is how computer reads. Have firmly been established as the state-of-the-art models in sequence modeling, mainly due to their in-context learning and ability to learn at scale. The primary building blocks of transformer attention modules functions as an associate memory blocks. Okay. Where they learn to store key value associations and retrieve them by computing pairwise similarity between queries, i.e. search singles, and keys, i.e. context. Of course, naturally. Accordingly, by design, the output of a transformer is exclusively conditioned on the direct dependencies of tokens in the current context window. This accurate modeling of dependencies, however, comes with quadratic time and memory complexity in terms of context length. In complex real-world tasks, e.g. language modeling, video understanding, long-term time series forecasting, the context window can become extremely large, which makes the applicability of these transformers challenging, the T in GPT. To overcome the scalability of transformers, recent studies aim to design different variants of linear transformers. Is there something here that was supposed to be? Is it not actually here? We can keep this. Transformers. It just didn't divide on the page. You know what I mean? Sorry, it just whatever. It didn't parse the PDF right. No big deal. Okay, where softmax is replaced by a kernel function in attention, resulting in a significant drop in memory consumption. Despite efficiency and ability to scale in a longer context, linear transformers do not show competitive performance compared to transformers, as the kernel trick makes the model a linear recurrent, or in which the data is compressed into a matrix-valued states. Dude, so many references, okay? That's Karpopoulos et al. 2020. This, however, brings a contradictory factor about linear recurrent or linear transform models. On one hand, we use linear models to enhance scalability and efficiency, linear versus quadratic complexity, whose advantages is appeared for long context. On the other hand, a very long context cannot be properly compressed in small value, vector value or matrix valued states. Okay. I'll just read it with all the proper words. Furthermore, beyond efficiency, most existing architectures ranging from Hopfield networks to LSTMs, transformers, face challenges when dealing with generalization, length extrapolation, and/or reasoning, all of which are inseparable parts of many hard real-world tasks. Although these architectures draw inspiration from human brains, each of which are missing a crucial component for the learning process, such as short-term memory, long-term memory, and meta-memory, attending to the current context. That's how our human brains work. We have long-term and short-term memory and meta-memory, apparently. How these components are interconnected systems that can operate independently and or the ability to actively learn from data and memorize the abstraction of past history. We argue that in an effective learning paradigm similar to the human brain, there are distinct yet interconnected modules, each of which are responsible for a component crucial to the learning process. Totally. We're slowly figuring out how to re-engineer consciousness from the ground up, and it's going to be used for AI so they can say funny things on Twitter. Memory perspective. Memory as a fundamental mental process is an inseparable component of human learning. Without a properly functioning memory system, humans and animals will be restricted to basic reflexes and stereotype behaviors. I want that. I want animal AI, purely instinctual, reacting to whatever I ask it, I poke it, it does something. Now, accordingly, memory has been an inspiration for many seminal research in learning literature, Hopfield networks, LSTMs, and transformers. Taking inspiration from the common definitions of memory and learning in neuropsychology literature, most existing architects consider memory as a neural update caused by input and define learning as a process for acquiring effective and useful memory given an objective. That's interesting. Okay, let's take that here. Memory as a neural update caused by input. Defined learning. How do we get smarter? We get smarter through memories. How do you get memories? Only through inputs that come in. Okay. In this perspective, recurrent neural networks, RNNs, can be defined as models with a vector value memory module M, also called hidden state, with two main steps. Given a new input, xt, at time t, the model updates the memory using a function. Function mt, is it -1, comma xt? With compression, retrieves the corresponding memory of an input, I don't know. Retrieves the corresponding memory of the input using a function, mtxt, see for details. Similarly, transformers can be seen as architectures with a growing memory in two similar steps. That is a pair of key value matrices acts as the memory's model, and the model updates the memory by appending the key values of the memory without compression, and retrieves query vectors corresponding memory by finding similarity of a query and key vectors, which is often used to weight the value vectors for the output. Okay. This perspective can help us better understand existing paradigms. There are critical differences in design more effective architectures. For example, the main difference between transformers and linear transformers is the memory structure as well as the memory updating step, in which linear transformers compress the historical data into a fixed size matrix value memory while transformers keep all the historical data with context layers without any compression. Oh. While both linear transformers and linear RNNs, including state space models, compress the information in a memory update step, the critical difference lies in the structure of the memory. Whereas linear RNNs versus linear transformers use a vector value memory versus a matrix value memory. Therefore, this perspective motivates us to ask question 1, what constitutes a good structure for memory? Question 2, what is a proper memory update mechanism? Question number 3, what is a good memory retrieval process? Beautiful. Yes, these are the questions we must answer in life. Fundamental questions of life. Now, will we figure these out today? Are Titans the answer to these things? I don't know. Maybe they are. Maybe they're not. I don't know. What constitutes a good structure of the memory? How do we structure the memories? Long-term, short-term, meta-memory. What is a good proper memory update mechanism? When do we save those new memories? How do we decide where to save those new memories? How do we decide what of that information we should compress? What should we not compress? How do we, I don't know, do some sort of transform, massaging, cleaning update? I don't know. What is a good memory retrieval process? When do we know to grab those memories from short-term, long-term, etc.? What inputs would make us say, hey, we need to grab that particular memory? Okay. Now, revisiting our understanding of human memory, it is neither a unitary process, nor it serves a single function. In fact, memory is a confederation of systems, e.g. short-term, working, and long-term memory, each serving a different function with different neural structures, each capable of operating independently. This fact motivates us for question 4, how to design an efficient architecture that incorporates different interconnected memory modules. Finally, you gotta end all the way, this is all the way to here, all the way to here. Finally, storing a memory is a neural process that inquires to encode and store the abstraction of the past. Oh, how do we encode and store the abstraction of the past? Encoding and storing abstractions of the past. Nothing like encoding and storing the abstractions of the past with some friends on a Saturday night. Right, see, that's a tweet right there. See, I wrote that, okay? Okay, so how to design efficient architectures that incorporate these different modules of interconnectivity. And then finally, is a deep memory module needed to effectively store... what is a deep memory module? Effectively store and remember the past? I don't know. I actually don't know. Contributions and roadmap. In this paper, we aim to answer the above 5 questions by designing a long-term neural memory module that can efficiently and effectively learn to memorize at test time. What does test time mean? Test time means when I'm quizzed on something, then I'm met. What do you mean? What does that test time mean? New section. Vegan questions. I'm vegan. This will be a section called tweets. What is test time? How can I build my own Titans? Also, whatever song we're listening to is just lovely, delightful. Room 136, perfect. A perfect title, perfect amount of information I needed to know there. Okay, so neural memory. We present a deep neural long-term memory that is as a meta in-context model learns how to memorize, store data into its parameters at test time, inspired by human long-term memory system. Okay. We designed this memory module so an event that violates the expectation becomes surprising is more memorable. Oh dear. Oh, that's quite interesting. That makes sense. Because what was the original quote by Samuel? We got to go memorize again here. Concepts. Neural memory. What is neural memory? A deep neural long-term memory that acts as a meta-context model, learns how to memorize, store data into its parameters at time. It learns how to store them. That might change what the data looks like. Inspired by a long-term memory. And we designed it specifically so that if something is surprising, that it's more likely to be memorable, okay? Because we have to answer this question of when do we effectively save what memories. To this end, we measured the surprise of an input with a gradient on the neural networks with respect to its input and associative memory loss, okay? To better handle limited memory, we present a decaying mechanism that considers the proportion of memory size to the amount of data supplied, resulting in better memory management. We show that this decay mechanism is in fact a generalization of the forgetting mechanism in modern recurrent models. Duh. I mean, come on, we've all read Dow and Goo. We're not dumb. Interesting, we find this mechanism is equivalent to the optimizing a meta-neural network with a mini-batch gradient descent, momentum, and weight decay. I mean, I was actually going to guess that. If you're following the steps, if you're following along, these things kind of seem obvious, okay? So building a pause in the tensorizing mini-batch gradient descent to use more matmul operations et sun et al. 2024. We present a fast and parallelizable algorithm to train our deep neural long-term memory. I mean, stuff's all, once you put out the basic ideas, it all feels pretty obvious what they're saying here. Okay, let's keep going. Titan architectures. After designing the long-term neural memory, an important remaining question is how to effectively and efficiently incorporate memory into deep learning architecture. We present Titans, a family of deep models that consist of 3 hyperheads. Core. This module consists of a short-term memory that is responsible for the main flow of processing data. We use attention with limited window size. Long-term memory. This branch is our neural long-term memory module that is responsible to store and remember long past. Persistent memory. This is a set of learnable but date-independent parameters that encodes the knowledge about a task. Interesting. Finally, as a proof of concept, we present 3 variants of the Titans, in which we incorporate memory, context layer, and a gated branch. Experimental results. We perform experimental evaluations on language modeling, common sense reasoning, recall-intensive needle in a haystack, time series forecasting, and DNA modeling tasks. We observe that the Titan architecture outperforms all other recurrent modern models, as well as their hybrid variants, combining the sliding window attention across a comprehensive set of benchmarks. Furthermore, Titans outperforms transformers with the same context windows and show competitive performance with transformers that use the entire context. This results are achieved while, contrary to transformers, Titans can scale to much larger than the 2 billion context size windows. So there you go. Okay, we win. We are better. Okay, I'm only on page 3. It's probably going to be a 2-parter. We've got to do a multi-part. I can't have these videos being too long. We could do it all in one video, but we're going to do 2 parts because I got to get back to coding. Okay, I got to actually write some of this AI stuff. I got to learn what this math actually says. Oh God, see, this is when it's time to run away. Oh God, what does that say? Now, preliminaries. In this section, we'll discuss the notation and some background concepts we will use in the paper. Yes. Now, anytime you get to a section that is about preliminaries, you know we're in trouble here. Okay. So this might be actually the spot to stop. And we'll do the first intro for the 15. It'll be a short little 15-minute video, and then we can try and tackle this. So this is the notation section. Now, this is the learning to memorize at test time, and it really is giving us some math here. So I think what we'll try and do, because that was a tough one. It was okay. We got the base start. I think we'll come back tomorrow on preliminaries, and we will try a little bit to understand the math. We'll take a little detour. It might take us a minute, and then we'll continue on. This might be a multi-part series. Maybe I mix some other rants in here. Maybe I do a long one next time. But that was it. We got some things floating in the head right now. I don't want to make these videos too long. So this paper definitely seems interesting. It's definitely mathematically over my head. Right, I'm a person hooking up APIs. I'm the dummy pulling down GitHub libraries and just writing dumb bots, hooking stuff together. So I'm not no math actual genius here, but we're gonna learn it together. I'll be back tomorrow. Thanks everyone. You got any questions? Put them